Good morning, everybody. My name is Rob Brown. I'm the engineering trainer here at Allied, and we're here to talk to you today about one of our newest products, the TA Pro. We have a short presentation about the product to talk about some of the details about it, and we have some demos to run for you. But before we get started, I want to point out to you that we have an offer available for you, that if you need help with the spindle, if you just go to alliedmachine.com/pro and fill out the form there, we can get you a free water bottle for signing up for more information. So this will allow you to connect with your local Allied field support staff for a free homemaking consultation. Whether you need help with troubleshooting homemaking at the spindle or would like to request a free demo with your local field sales engineer, that's what this form will help you out with. So we'll remind you again at the end of the presentation, but that's something we got going on for you today. So let's get started on talking about what TA Pro is. Okay, TA Pro is a product that allows us to become very specific with ISO geometries. It's something that we're doing to make this tool selection process significantly simpler. So we're following the ISO specifications. That would be like P for steel, K for cast iron, N for aluminums and non-ferrouses. And it's a color-coded thing as well. Blue for steel, red for cast iron, green for products like aluminum. So it follows the ISO material classification, which most people are familiar with. It makes it much simpler to do the selection process. Since the geometries are specified for those specific types of materials, we get much better chip formation in those materials. And it offers a lower cost per hole by giving you maximum tool life and also allowing higher penetration rates. Okay, so something that we did differently with the TA Pro product is that we did improve the notch point geometry on it. By having a redesigned notch point, it improved the strength and the chip flow capabilities of the notch point geometry, but it still offers excellent centering capability and lower thrust and horsepower requirements versus a tool without that enhanced notch point geometry. So looking at the geometries themselves, we're going to speak first about the P geometry, which is for steels. It's designed to provide increased penetration rates and improve tool life in steel applications. The geometry in the edge prep offers excellent chip control because it is specifically designed to be run in steel applications. And it features our multi-layer AM300 coating to increase heat resistance and improve tool life in those applications. So this is a carbide tool. The P, K, and N are all carbide substrates. So what we've done is we have a coating, substrate, and geometry that's specifically designed to enhance the performance of the tool in those materials. So next is the K for cast iron. So this would be for nodular and gray irons, for example. The geometry offers maximum tool life, helps minimize frittering at exit, and improve the whole finish itself. This uses TILN coating for improved abrasion resistance and increased tool life. Now the N geometry is for non-ferrous materials like aluminum, brass, things like that, copper. The geometry yields excellent chip control in those softer, more gummy materials. It's coated with TICN to minimize edge buildup and offer excellent tool life as well. Now for our X geometry, the X geometry is not an ISO specific geometry. It is actually a high-speed steel version of this. So if you have an application where increased toughness is something that is required, the X geometry will work for that. It offers improved geometry for good chip control in a variety of different materials. So instead of being ISO specific like just for steels, this is a more general purpose geometry, but you gain the advantage of a significantly tougher substrate. So that's going to offer you a longer tool life and good, what we call process security reliability for the most challenging applications. This is coated with our AM200 coating, which is also a multi-layer coating. It offers good heat resistance and good lubricity and a wide variety of different materials and offers increased tool life. So along with the inserts that we've improved for TA Pro, we also redesigned the holders to improve the coolant design, which improves coolant flow by 25%. So what that does is helps you in applications where maybe you don't have a high pressure or a high pressure flow situation. So by opening up the coolant hole sizes, it allows you to get more coolant flow at the given pressure that's available to you. Because whenever you're talking about successful high production drilling, we need to form the chip, and then we got to get the chip out of the hole. And the way that we get the chip out of the hole is by the flow that we get through the tool. It offers improved holder rigidity by having different sub-series within a series of tool. So that gives us the ability to maximize the strength of the tool for the application that you're running in. It also has a redesigned flute that maximizes chip evacuation, and that's available in lengths up to 15 times D. Okay, so when we're looking at those different body diameters, we want to make sure that we have the correct insert and body combination. So in the example that's shown on the screen there, you can see there are some that are highlighted in white, and then some that have the gray background on it. That would be the different sub-series, because you can see there's an A and a B, and the A would be the smallest body diameter, and I can use a B series insert in an A series body. I just wouldn't get the maximum rigidity out of it, but I can't use an A series body or A series insert in a B series body because the body would be bigger than the cutting tool. So that's all shown to you in the catalog whenever you go through that to try to select the proper tool, and it offers you a nice simple way of making sure you don't get that mixed up. So looking at the speeds and feeds of the TA Pro product, it's similar to other speed and feed charts that Allied puts out. It makes the finding of the different materials that you want to run and the speeds and feeds that you want to run rather simple. Following that ISO classification, it is color coded as well as calls out like P for steel, K for cast iron, and so forth. So it allows for a simple selection of the insert, because obviously if you're running steel, which is P, you're going to run the P geometry TA Pro. For longer tools, 7 times D and above, we do have speed and feed reductions based on the length of the tool. For 7 and 10 times D, you're going to reduce speeds and feeds by 20%. For the 12 and 15 times D tools, you're going to reduce it by 30%. And so you would take the speed and feed that's recommended, put those multipliers to it, and that's what you would apply to those longer tools. Okay? So along with that, since the tools do go up to 15 times D, what we consider a deep hole drilling application is anything 9 times D and over. So whenever you get longer than that, we want to make sure you follow the Allied deep hole drilling guidelines. And the way you're going to know if your application applies to is when you're selecting the holder. If the item number for the holder is in an orange box, that's an indication that we want you to follow the deep hole drilling guidelines. And there's always going to be a note at the bottom of the page. It'll refer you to the proper page for the deep hole drilling guidelines. In this case, it's A2564, and that's what we're going to show you next, are the deep hole drilling guidelines. And what we do is we have you start off with a short link drill, and we do that for 2 reasons. One is the short link drill establishes the hole, so you get a nice true position, no taper, straight hole. So it gives you a good starting condition for the application. And then the other thing is it basically turns your workpiece into a bushing for that longer tool when it comes in. So the second step is that longer tool is going to come in running at 50 RPM max to minimize whip. Once it gets down to about 1/8 inch from the bottom of the hole, you kick up the speed and feed to the recommended based on what the book told us to do, which is the book recommended speeds and feeds times that multiplier based on the length of the holder. Then we're going to drill the hole. Whenever we finish up and go to retract out of the hole, we're going to go back to that slow RPM again so it doesn't whip whenever you retract out of the hole. The last demo that we run for you today will have a deep hole drilling application, and we'll kind of run through this again as we run that demo. And then finally, we're talking about just kind of a keystone or a cap for what we've got going on with the TA Pro product. The TA Pro product runs in a wide range of operating parameters. You can do high penetration rates, or you can slow it down a little bit to get a more reliable process. And in some situations, you can do both. You can run it fast and have a reliable process. It does offer improved chip formation over our previous designs that we've had historically. We give you more holder options to maximize rigidity. That's at multiple diameters within the series of the different bodies. We just got to make sure that the insert and the body are compatible to each other. With those changes to the coolant hole design of the product, we get increased coolant flow, which is always going to make it easier to evacuate that chip. So that gives us the ability to run a higher penetration rate and still have a nice, reliable process. So that is our presentation about what TA Pro is. So So now we're going to get ready to run some demos. And we're going to start off with demo number 1 is running 4150 alloy steel. We always use that as a good benchmark to kind of show you what we could expect to get, and it's a nice point of reference as we look at other materials as we go through the process. What we're going to be using here is a 9/16 diameter TA Pro P geometry insert, and that diameter in metric is 14.29 millimeters. Speed and feed we're going to run the tool is basically right out of the book, which is 340 surface feet a minute and 7 thou per rev. And the coolant pressure is set to 300 psi. So you can hear Dave's running the holes behind me here. So he's going to get things gathered up so we can take a look at them and see what we have to work with. Let me come over here and get this. Safety glasses on. There we go. And what we're going to see is a nice, small, manageable chip, which is what we want the tool to do for us, okay? Because, and here's the chip form that we get. This is, once again, TA Pro P geometry running in 4150 alloy steel. The hardness of the material is 28 to 32 Rockwell in hardness. And you see we get a nice, small, manageable chip. There's no stringers, nothing like that. It's going to be easy to evacuate that chip. And remember, with that improved holder, we also have larger coolant outlets, along with the enhanced flute design on the tool to maximize the ability to evacuate the chip. Okay, so that's demo number 1. Let me show you what the holes look like here to show you what the quality is. Okay, and once again, this is 14.29 millimeter or 9/16 of an inch in diameter, and the depth of the hole is 1.5 inches. So you can see the quality of the hole is nice and clean. There's not a lot of gouging or anything like that. The surface finish looks pretty good. And then on the back side, there's a small amount of an exit burr. Let's see if I can kind of get you to see that a little bit, but the exit burr is quite small. Looks a bit worse than it is just because of the fuzzies that got a hold of it there, but you can get this hint of what we got going on. And that's what we got in 4150. So as I said, that is what we do. It's a good benchmark, so as we get into these different materials, we can look at how that performed in relation to the 4150, because we know the 4150 is a good chip forming material. It creates a nice finish, so it's a nice thing to use as a point of reference as we look at the other applications. Okay, so for demo number 2, what we're going to do is we're going to switch from a TA Pro P geometry insert, which, remember, that is a carbide insert. We're going to switch it from that to a X geometry tool, which is the high-speed steel version, and we're going to change the size on it as well, because what we ran in the first application was a 9/16 diameter. What we're going to do for demo number 2 is we're going to run a 13/16 diameter, which equates to 20.64 millimeters, running in 1018 low carbon steel that's about 170 Bernal, somewhere in that neighborhood. Speed and feed for that's going to be 300 surface feet a minute and 12 thou per rev. And throughout these demos, we're going to run the coolant at 300 psi, a nice consistent number all the way through this. So once Dave gets this ready, we're going to drill 2 holes in the 1018 so we make sure we get enough chips to show you, and also give you the opportunity to look at it, how it does in a couple of different holes instead of just a single one. So this is an X geometry high-speed steel insert. So the reason why you would want to use high-speed steel versus the carbide is if you're in an application where there is issues with voids, porosity, lack of rigidity, for example, something like that. High-speed steel might be something that you want to look at. But if you have a nice rigid setup and everything, obviously you'd want to try to stick with the P geometry if you can, because you're going to get improved penetration rates with it. But the X geometry gives you that reliability that sometimes carbide doesn't like to provide for you. So Dave, if you're ready, let's go ahead and run demo number 2. Once again, 1018 low carbon steel, about 170 Bernal in hardness, running an X geometry, which is high speed steel, at 300 surface feet per minute and 12 thou per rev. So there we go, and that's running about 65% load. Okay, so we're going to drill hole number 2. Then whenever that's done, just like we did with the 4150, we're going to gather up some chips and take a look at them and see what we got going on there. Okay, now we don't expect the chip formation for this to be quite as nice as what we get with the 4150 because, well, it's more gummy, it's less consistent in its design, so the chip form on it is not expected to be as good. But the idea is you get chip formation capability that is manageable. So this is what we get with the 1018. Okay, you can see there's some small chips, there are some pieces that are a little bit longer, but you can see they're pretty close to breaking. These longer flat chips are real common in 1018 low carbon steel. I mean, this is just what we see all the time. Because once again, the chip formation capability for that material is not nearly as good as it would be like for 4150 that's obviously heat treated quite a bit harder. Okay, so we're going to take a look at the slug here in just a second. Once Dave gets it blown off for me here, and we'll show you what the finish looks like, what the hole itself looks like, what kind of an exit burr that we get. Now, the thing to remember with this low carbon steel, and we've talked about this in previous videos, whenever you're talking about low carbon, it has more of a tendency to want to tear instead of a nice clean cut. So the surface finish is not going to be as high quality as what you get with alloy steel. And you can see that here. You know, it's what I would consider a more typical drilled finish. If I were to put it into a category, I would say we were probably somewhere in the neighborhood of maybe like a 150 finish, somewhere in that neighborhood. And then looking at the exit burr, it does make a bit more of an exit burr than what we saw with the 4150 as well. And you know, what you need to remember is with that more soft gummy material, since it has a tendency to tear, it's also going to deform and push a little bit more, so it makes a bit more of an exit burr than what you would see with, you know, a harder alloy steel. Okay? So now we're going to do something a little bit different because we're going to switch to nodular iron. So now chip formation really isn't part of the equation anymore because when we're talking about cast iron, it's a discontinuous chip forming material, which means it's always going to break a chip. Really what you're looking for whenever you're talking about nodular and gray irons is more how fast can I go and how long is the tool going to live, okay? So what we're going to use for this one, we're actually changing to a different series of TA Pro. We're going to go to a number 2 series, and this is going to be the K geometry, which is specifically designed for cast iron. And if you remember when we talked about it just a couple of minutes ago, it's got a carbide substrate. It has a geometry that's uniquely designed for nodular and gray cast irons, and it's coated with TiALN coating. Speed and feed we're going to run this tool is 500 surface feet per minute and 16 thou per rev. And we're going to drill 2 holes, and once again the diameter of the drill is 1 inch. It's a 25.4 millimeter diameter. Okay, so whenever Dave's ready to go for that, we'll go ahead and run in. Sounds like we're ready to go. So here we go. So once again, it is a carbide tool running 500 surface feet and 16 thou per rev. So drilling the 2 holes didn't take too long. And we'll gather up some of the chips, but we already know the chip formation is going to be good for this because it's cast iron and that's what you get. But, you know, the nice thing about the situation is with this is now what we need to look at is, so how long will the tool live at those kind of speeds and feeds? And obviously, you know, for this presentation today, we're not going to be running for tool life. As you can see, here's the chip form that you get with, and this is once again nodular cast iron. It's about 200 Bernal in hardness. Okay, so once Dave gets that slug out, we'll take a look at the quality of the hole and see what the breakout looks like at the bottom for the through hole application. Okay. So he's getting us wiped up here. He's got to blow it off before I show it to you. And we'll get it from him here and see what that looks like. Thank you, sir. Okay, so once again, this is a 1 inch diameter hole, so this one's a little bigger yet. And you can see the quality of the hole is actually quite good. Okay, no tear marks in it or anything like that. It's a nice smooth finish. Okay, try to get it so you can see. There's a nice shot of it. You can see. Let's look on the back side. Once again, the exit burr or the breakout that's created from it is quite small. I mean, there's a little bit of fuzzy on it from wiping it down, trying to get the coolant off of it. But you can see that it doesn't have a large exit burr. Definitely a lot smaller than what we saw with the 1018 low carbon that we ran just a few minutes ago. Okay, so now we're going to run in the end geometry, which is specifically designed for non-ferrous materials like brass and aluminum, copper, those kind of things. And we're going to be running in 6061 aluminum. That's about 80 to 100 Bernal in hardness. The diameter of the tool, we're going back to that 9/16 diameter, which is 14.29 millimeters in diameter. Speed and feed we're going to run is 900 surface feet per minute and 11 thou per rev. Okay. Now with the end geometry, once again, carbide substrate, geometry specifically designed for non-ferrous applications like aluminum, and it's coated with TICN coating. The main reason you're going to use TICN here is because TICN does a really good job of resisting buildup edge, and that's a really common problem in a lot of aluminum applications, is you get a lot of chip weld that goes on, and then TICN resists that pretty well. So even at this high speed and feed that we're going to be running though, we're still going to run that 300 PSI of coolant, because with those increased coolant outlet holes in the TA Pro product, the lower pressure coolant still delivers quite a bit of coolant to the application. That makes it so we don't have to worry about running, you know, an example like 1,000 PSI in order to be successful here. So once Dave's ready to go, he's giving me the thumbs up, we're going to go ahead and run this. We're actually going to do 4 holes in the 6061 because this isn't going to take terribly long, and it'll give us the ability to make sure we get a hold of some chips to show you underneath the screen there. So here we go, 900 surface feet, 11 thou per rev, 9/16 diameter with an end geometry TA Pro insert. So here we go. All right, so the spindle load's about 65-ish%. It goes pretty quick because it's not in the cut for very long, okay? That's it. So we've drilled 4 holes with it. So we're going to give Dave a chance to kind of grab up a couple of chips here that I can show you. And while I'm showing you those chips, you'll get the part out of the machine so we can take a look at that and see how that came out. Okay, so here we go with showing you the chips. They like to stick to everything. So here we go. So here's the chips that we get in aluminum. Once again, this was running 900 surface feet, 11 thou per rev, 6061 aluminum. That's wrought. That's about 80 to 100 Bernal in hardness. So the chip form's really nice small chips, keeps them moving real good. So those smaller chips in concert with that increased coolant flow that you get through those larger holes makes it so chip evacuation is really not anything to be terribly concerned about in this application. Okay, so let's take a look at the quality of this one. Okay, and here we go with the 6061, and you can see like it's a drilled hole. You're not going to mistake it for something that had a reamer going through there, but the quality of the finish is fairly consistent, okay, for all 4 holes. And looking at the breakout on the bottom side, it does create a little bit of an exit burr, but nothing too extreme to get overly concerned about, okay? So that's 6061 T6 aluminum. All right, so this brings us to our last demo for the day. So what we're going to do here is we're going to do those deep hole drilling. We're going to be using a 9/16 diameter TA Pro P geometry insert. We've got 2 different holders we're going to use. We're going to use a 3x D holder and a 10x D holder to drill this hole to depth. The other applications we've all run are 1.5-inch deep holes. This is going to be 4.5 inches deep. The material, once again, is 4150 alloy steel, 28 to 32 Rockwell. Diameter of the cutter is 9/16 of an inch. Speed and feed we're going to run is 238 surface feet and 5 thou per rev. So what we had to do here, since it's a 10x D holder, we took the book recommended speed and feed, which if you remember in demo 1 that we ran was 340 surface feet and 7 thou per rev. We took those numbers and multiplied them by 0.8 for a 20% reduction in speed and feed. That's where we come up with 238 and 5. Okay, so the first thing we're going to do is use that 3x D holder to establish the hole, just like step 1 in the deep hole drilling guidelines. You can run that at the 340 and 7, but we're going to run it at 238 and 5 because we're going to act like we haven't done this before, and we want to check to make sure our chip form is still good, because we did run a different speed and feed. And obviously if the chip formation isn't good in the shorter drill, it's going to be really unsatisfactory when you go in with the deep hole drill. Okay, so Dave, if you're ready, we're going to go ahead and drill the pilot hole first at 238 surface feet, 5 thou per rev, and take a look and see what that looks like. Okay, and then once we've determined that we're okay with that, then we'll come in with the longer tool following those deep hole drilling guidelines. Okay, so we're just drilling a hole a couple of diameters deep, and all we're going to do is I'm just going to grab a couple of chips here and take a look at them and make sure that we're okay with them. Okay, and I can tell you right now, they're just fine. I'm not going to put them on a napkin. I'll just bring them over and show them to you under the camera here real quick so you can see what we got. Now, we don't have a lot of chips to show, but you can see like the chip form on it. We're still getting excellent chip formation, so we don't need to worry about the when we come in with that longer tool. So now he brings that 10 times D tool into the spindle, and what we're going to do here is steps 2 through 6 on the deep hole drilling guidelines. We're going to bring that long tool in. As we bring it in and we start to spool it up, it's going to run at 50 RPM. Okay, and that 50 RPM is to keep the tool from going into whip before we have the margins engaged in the cut, because we're going down into that pre-existing hole and kind of treating it like a bushing. Okay, so now that we're down towards the bottom, the coolant's going to kick on, the RPM is going to come up to the speed and feed that it needs to run, and we're going to run the deep hole drill. Okay, so while this is running, the things that we want to keep an eye on is the coolant still coming out well, which it is. What's the tool sound like? It's a nice steady pitch as far as the sound that it's making. There's no low pitch grumbles or anything like that, and you're not seeing any vibration out of it. Because whenever you have chip packing issues with a deep hole drilling application or any drilling application, you know, you can see it, you can hear it, you can feel it. Okay, so that ran just fine. Now I'm not going to take the part out and show you because it's a little heavy to do that, but we're going to gather up some of the chips and show them to you here. And another thing to note is that the chips are basically all over the table of the machine, so it makes it so what that tells you is that the chips aren't just barely coming up out of the hole and then not making any more propulsion than that. So we see we got nice small chips, which is going to be really, really good for deep hole drilling because the chips are small and light, but yet they still have the right shape for the coolant to get a hold of it to propel it up out of the hole. It's going to be a good deep hole drilling application. Okay, so that basically takes care of our demos for today, and hopefully this helps you understand a little bit about what TA Pro can do for you as far as in a variety of different materials. The key things to remember: it's a much simplified system is trying to choose the right tool for the job. You're just going to match it up based on your ISO classification. And make sure that you get the holder that matches up to the insert that you're going to run, so that way you don't have an interference there. So just to kind of remind you, I said something about it at the beginning of the program, but I just want to kind of reiterate to you and grab my sheet so I make sure I tell you the right stuff. That if you need help with the spindle, if you go to alliedmachine.com/pro, we're going to and request either a demo or a consultation with one of our field sales engineers. By filling that out, we're going to send you a free Allied water bottle, and you'll hear from one of our field sales engineers to take a look at your application and help you with the selection process, maybe recommend some different tooling, speeds and feeds that you need, that kind of stuff. So whether you need help troubleshooting hole making at the spindle or like to request a free demo with a local field sales engineer, this is going to be the mechanism that's going to help you make contact with Allied so we can follow up with you and see what we can do to help you do better with your drilling applications. So thank you for your time today. Hopefully it's been educational for you. And once again, stay safe out there, and we'll see you next time. Thanks.